Hello everybody, it's Mrs. Pound and we are covering chapter 37 on electromagnetic induction. This is another short chapter that will have just 2 videos. So our objectives today are to describe how voltage is induced in a coil of wire, relate the induced voltage in a coil to the number of loops in the coil and the rate of change of an external magnetic field through the loops, describe a generator and how it works, and compare and contrast motor effect and generator effect. So our first topic is electromagnetic induction. So what is it? This is the phenomenon of inducing a voltage in a conductor by changing the magnetic field near the conductor. So when we induced charge before, that meant that we changed the field around it to produce a voltage, and it's the same idea here, except for now we're using magnetic fields to do this. Voltage and current can be created in a wire by moving a magnet in and out of a wire coil. So here in the background is a wire coil. I could create a voltage and current in this, so electricity, by passing a wire in and out of it, and I'm going to show you that in class. So a magnet is moved in and out of a coil of wire connected to a high resistance voltmeter. If the number of coils is doubled, the induced voltage also doubles. So that's a pretty cool phenomenon. So remember we said that the magnetic field is increased in electromagnetic from the last chapter by increasing the number of loops. Well, we can also increase the voltage because we're increasing the magnetic field, and it doubles as well when we double the loops. So more loops equals more induced voltage. And a magnet is moved in and out of a coil of wire connected to several lamps. If the number of coils is doubled, the resistance you feel increases. If you add more resistance, if you add more coils, it increases too. So it makes it harder to move the magnet. And the reason is the law of conservation of energy. If you apply more effort or work, you get more energy out. So if you add more lamps, you need more energy, so you have to apply more work. So more loops equals more current, equals a stronger magnetic field, equals stronger repulsion. That is also why you need to do more work, because you're getting a stronger magnetic field there. And also, faster movement is more induced voltage. So the faster you move that magnet in and out of the wires, the more voltage you'll get. So let's take a look at Faraday's law, which is based on these ideas. So Faraday's law says induced voltage in a coil is proportional to the product of the number of loops and the rate at which the magnetic field changes within those loops, which makes sense based on what we were talking about, that we were saying if you increase the loops or you increase the rate at which you put the magnet in and out of the loops, you'll get more voltage. So what this means is change in this product can be caused by rotating the coil, by changing the shape of the coil, or by changing the magnetic field strength, all 3 of those things. Now, some places that we use this for detecting weapons at airports using metal detectors. So how does that work? When an iron object enters the interior of a current-carrying coil, the magnetic field lines are distorted by the presence of the iron. This changes the magnetic field in the coil, which is sensed as an induced voltage and sounds an alarm. So if you've ever walked through a metal detector, they're these big rectangles that you walk through. There are coils going around you, and when you walk through those with metal, it causes an electric current that sets off an alarm, okay, because it induces a voltage in that machine. And so that is how that works. And then they know you have metal and you have to empty your pockets and all that, and they have to figure out what is causing that alarm to go off. Another place this works is if you've ever been at a stoplight where they tell you you have to stop at a certain point to change the light. There are actually coils underground, underneath the car, that by you driving over those coils, you are inducing a voltage, causing a current that lets the signal know that it has to change. So, generators and alternating current. Okay, what a generator is. A generator is a machine that produces electric current by rotating a coil within a stationary magnetic field. So on these windmills, inside of that box there is a generator. And by the turbines spinning, they rotate a coil within a magnetic field, which induces a voltage and causes current to flow. And so that produces electricity. The same way, this works the same way for when they're using coal or nuclear power, except for what they do is they heat up steam and the steam goes through turbines. This is the same thing that happens at an electric power plant that uses coal or even nuclear energy. What they do is they heat up water, which produces steam, and the steam rising turns turbines that turn a generator. It's the same idea. So a generator is used to light a bulb, and energy for lighting the bulb actually comes from another source. The source is wind, water, steam from fossil fuels or nuclear energy, like I talked about before. Here with the water would be our hydroelectric plants. They also turn turbines that are hooked to a generator. Now, the way this works, and we're going to get into this a little bit later as to why alternating current works the way it does, but when that turbine turns and the coil turns, it actually produces alternating current. So, motor and generator comparison. The underlying principle for the operation of an electric motor is that a current-carrying wire is rotated in a magnetic field. So, where the generator, we said, which if we look at this fan, looks an awful lot like a turbine. Well, it is, except with a turbine, the wind is turning and it's producing electricity. With this, the electricity is turning the fan blades. So you might look at this fan and say, looks an awful lot like a turbine. Well, you're right. With a turbine, it is the wind turning the blades that produces the electricity. With a fan, it's the same device, but it's the electricity turning the fan blades that then causes the fan blades to move. So it's just the opposite way around. And so in this case, there is a current carrying wire, and because it's in a magnetic field, it starts to rotate and it turns those blades instead of the other way around. So a motor changes electrical energy to mechanical energy or work. And some examples are a blender, a washing machine, dryer, microwave turntable, and fan. Where a generator takes mechanical energy, work, and converts it to electrical energy. So if you are listening here, I want you to draw an arrow between the generator and the motor, and on that arrow, like a double arrow, I want you to write opposites, okay? Opposites on that double arrow. So our objectives today were to describe how voltage is induced in a coil of wire, relate the induced voltage in a coil to the number of loops in the coil and the rate of change of an external magnetic field through the loops, describe a generator and how it works, and compare and contrast motor effect and generator effect. So don't forget your 5 questions, and there will be one more video for this chapter.